Hello, this is Teach Nichols, and this video is on light. The essential question is, what is light, and how do the wave properties of light impact what we see and observe? So if you look in a physics textbook, it will say that light is a series of electric and magnetic fields moving through space. Fields or force fields are a concept in physics that's a little bit abstract. It's kind of like a way objects communicate with each other, communicate their fundamental properties. But in any case, for this class, you can view the fields as the wave. It's kind of interesting that they go together, electricity and magnetism. That's something that can be observed in many facets of physics, especially if you guys kind of move up in more complex levels of physics. Light is transverse. That means those electric and magnetic fields jiggle perpendicularly compared to the direction the light is moving. And we'll do a demonstration in class to show you how they know this and how they can prove it. One fun fact about light is that it does not need a medium to travel through, which means it can actually move through a vacuum, unlike all the other kinds of waves that we've been discussing. So like all waves, it is useful to discuss where does the wave come from. And for light waves, many of them, most of them, come from electrons inside the atom. And those electrons exist in different orbitals or layers in the atom. And as they jump from one to the other and change the amount of energy that they have based on their position, that extra energy is released in terms of light. Because they come from electrons, light is often called an electromagnetic wave, and also because it's consisting of electric and magnetic fields. So the word light can be used interchangeably with the word electromagnetic wave. So as I mentioned in an earlier slide, light is special in that it doesn't have to have a medium, but it can travel through medium. It can travel through different materials. It actually can go through anything, and even the absence of anything. Of course, different media are going to have different properties. The light is going to respond differently. For example, some media will dampen different frequencies of light out. And also, just like with all other waves, the speed of the light depends on the medium that it's going through. Opposite from sound waves, though, light actually goes slower through solids and liquids, and it actually goes fastest when there is nothing for the light to run into and sort of be absorbed with. So the speed of light in a vacuum, which is through the emptiness of space, is 300 million meters every second. And that is been shown to be nature's speed limit, which means that nothing in the known universe can go faster than the speed of light in a vacuum. So it's kind of an important number and factors into a lot of advanced physics as well. We're not going to spend as long on how eyes work as the amount of time we spent on how ears work, but in general, in order to see something, a little piece of light from that object has to go through this hole in the center of your eye. And it goes through that hole and it hits the back of the eye in a location known as the retina, and that's where you basically have light detectors that can detect different properties of the light. So similarly to sound, your eyes are only capable of detecting certain wave properties. And actually, you detect the same two things about light as we detect about sound with our ears. We have special cells not known as rods and cones that let you determine these properties, the frequency and the amplitude. The rods can differentiate between high and low amplitude. Sometimes we talk about them being sort of black and white. They just tell us how much light is there without telling us anything else about it. And the cones are the cells that detect the frequencies of light, which we'll talk about in just a minute. But we have a lot more rods than cones because actually it's really mostly important that humans can tell bright versus dim, more important than anything else. So light amplitude is energy, same as it is for every other wave. Although there is a tiny nuance with light, which if you take AP Physics, you'll discover that Albert Einstein and a guy named Max Planck discovered. In any case, in general, amplitude is energy, and that means that we have more of these electric and magnetic fields. Humans interpret more amplitude as brighter lights, so the light bulb on the left has lower amplitude and the light bulb on the right has a higher amplitude. Those cone cells that detect the light frequency are responsible for all of the beautiful colors in the world around us. So humans actually interpret different frequencies of color. Color is to eyes as sound is to pitch. Um, so the typical human vision range is between 400 and 750 trillion hertz. When you think about how comparatively slow the vibrations of sound are, this is really overwhelmingly fast number of jiggles per second. And the different colors are the different frequencies in that range from purple all the way up to red. The purple or violet frequency is higher than the red frequency. That means the violet frequencies are vibrating more quickly or more hertz than the red ones. So there's this range of frequencies that humans can detect. And the chunk of light that our cones are sensitive to is known as the visible light spectrum. And it contains all the colors of the rainbow that you probably learned about in elementary school: red, orange, yellow, green, blue, indigo, violet. But there are colors outside of that frequency range that our eyes just aren't sensitive enough to detect, just like there are sounds that your ear is not sensitive enough to detect. And so those colors of light are invisible to humans, but that doesn't mean that they're not there, and that doesn't mean that they're invisible to other animals, etc. So gamma rays, X-rays, ultraviolet rays, infrared rays, and radio waves are all different colors of light that just are not detectable by humans. So those are all outside. You can see the visible light sits right here in the middle, and those other colors span the two ends of the spectrum. So it turns out that the human eye actually only can see three colors. And the reason is because it would be kind of unnecessary to have detectors for all of the colors in the universe. It would make our eyes really, really big. And actually, we can sort of do the same thing with just three colors and a really big brain, which humans tend to have compared to other animals. Um, so our brain can actually add signals of light to create colors, either colors in the rainbow or even some colors that are not in the rainbow, so kind of imaginary invisible colors, based on activating those different tones in different amounts. This is called color addition. So we have these three detectors, red, green, and blue. And if two or more of them are triggered at the same time, the brain sort of says, well, how much of this are we adding to how much of this, and what color does that mean we're seeing? So for example, if you have the red detector and the blue detector both being activated by a light, well, our brain actually invents the color magenta, which isn't even in the Roy G. Biv color spectrum. They call it this bright pink. If your brain is seeing blue and green at the same time, it invents the color cyan. And if we're seeing red and green at the same time, it thinks it's looking at yellow. This ends up being really useful kind of industrially, which I'll explain in class a little bit later on. And then, of course, like, what if we're seeing all three? What if we see red, green, and yellow in equal amounts? Well, our brain actually does something really interesting with that. It creates the color white. It's like, I'm getting all this light, this red, green, and blue. All my detectors are going, and I'm going to imagine this color that is called white. White is not in the Roy G. Biv color spectrum, so there's no pure white. White light is made up of all of the other colors of light. Um, so when the sun that creates white light around us, what you're actually seeing is an entire rainbow of color, and our brain just can't tell that those colors are separate. It just blends them all together into the single color called white. Now, most of the colors in the world around us are not created by combining light, because most objects don't actually make light. Um, Most colors around us are created when the sun shines its white light on an object, and then some light bounces off that object and goes into our eye. We actually call this light subtraction, because we're starting off with all the colors in that white. Remember, white is made a rainbow of colors, and the objects are actually subtracting or taking out all of the colors except the colors that reflect off. There are molecules known as pigments in most objects, and these are the molecules that specialize in kind of subtracting or sucking out different colors of light. And of course, they got to do something with that energy. They, generally speaking, turn it back into thermal energy. And so we'll talk later on about what kind of effect that has on the things around us. So light subtraction works a little bit different from light addition. Um, there are three primary colors for light subtraction, which you probably learned about in elementary school. You called them red, yellow, and blue, but actually the true um, primary colors of light subtraction are yellow, because that color basically subtracts out just the blue light, magenta, which subtracts out just the green light, um, and cyan, which subtracts out just the red light. So if you put a yellow pigment and a magenta pigment together, we've subtracted blue, and then the magenta subtracts the green, and so what the only color that's left to reflect is red. So in any case, you can see how we can make all of these different colors from light subtraction as well. If you put all three light subtraction pigments together, yellow, magenta, and cyan, in theory, it should subtract all the color, and then you're left with the color black, which is essentially none of those rods or cones in your eyes being triggered, everything sort of being absorbed by the object that it's going into. Okay, so please take a few minutes and revisit the essential question, which is what is light and how do the wave properties impact what we see? Thanks for watching.